which are commonly referred to as wind ripples. And the second example is the flexible gravity wave, meaning that this model is first written for the floating ice sheet. You can imagine an ice sheet on the top of the fluid being with gravity waves underneath and how it reacts. These two waves has been discussed by Professor Aquilas and Palu Emilien. There might be a little bit overlap, but I think it's sufficiently a different thing. All right, so this is my plan. Introduction for the nonlinear waves, nonlinear Schrödinger equation. Then I would like to talk about capillary gravity waves. So focusing dynamics of capillary gravity wave and the flexible gravity waves. This is a joint work with Professor Paul Milewski and Jean-Marc van den Block. All right, so what is the conventional wisdom for nonlinear waves? Take a linear wave equation and add a little dispersion, add a little nonlinearity. What do you get? You get solitary waves. The canonical example is the KdV equation, right? Celebrity KdV equation. Why do you get solitary waves? Well, the dispersion disperses, right? Makes the wave tends to spread out, and the Burgers type nonlinearity steepens the wave. You can drop the UXX term, and the left part is the implicit Burgers equation. You immediately know for most of the initial data, the waves tends to overturn, and the first order derivative blows up at finite time, unless the initial data is monotonically increasing, right? Okay, so these two effects, the dispersion and the nonlinearity, can miraculously balance and result in the square soliton solution. KdV and other equations of this type, you don't have to have UXXX. You can have Hilbert transform with UXX, second derivative, which is a Benjamin-Ono equation. You don't have to have UUX. You can have U square UX, which is also fine. All sorts of these equations arise when linear wave near the wave number k equals 0 are non-dispersive, which is called long wave approximation. Because you make an approximation near the wave number k equals 0, then the typical wavelength, which is measured in the background length scale, approaches infinity. So this is a long wave approximation. Therefore, the actual physical wavelength is not important. Only the ratio of the background length scale to the physical wavelength is important, which is the small parameter epsilon appearing in the equation, right? Okay. What do I mean by non-dispersive? Because we are considering dispersive equation, and the frequency is a function of the wave number. Non-dispersive point means if you Taylor expand the dispersion relation at this particular point, then to the leading order, omega is a linear function of the wave number. That means the tangent line at this particular point, at the non-dispersive point, goes through the origin. So this is the meaning of non-dispersive. And this is an example for the pure gravity waves in shallow water, which is a KdV regime. And the blue curve is the dispersion relation, omega versus wave number. And it is obvious that wave number k equals 0, the tangent line goes through the origin. So this is k equals 0 is a non-dispersive point. And there are several water wave problems where the linear waves are close to be non-dispersive at a non-zero wave number. The typical example is the capillary gravity wave. So this is a capillary gravity wave in deep water. This is the dispersion relation for capillary gravity wave, the blue curve. And it is obvious that the wave number k equals 0 at this particular point, the tangent line goes through the origin. So this point is a non-dispersive point. In this case, the wavelength is intrinsic because now you don't have the background length scale. So we have to stick on the wave number k equals 1 under my non-dimensionalization. So that's these two are different. This is long wave approximation, this is not. All right, so now that means the non-dispersive point can occur at the wave number k equals 0 or non-zero wave number. So what do they have in common? What they have in common is, in both cases, the phase speed, which is the speed of the propagation speed of the crusts, and the group speed, which is the propagation speed of the envelope. By definition, they are equal at the non-dispersive point because omega equals ck, right? This is what they have in common. And now, if you compute the group velocity in terms of the phase velocity, and you will see, because the group velocity equals the phase velocity, so that means either k equals 0, Cp prime is finite, or Cp prime equals 0. Okay. So that's the situation. So Cp prime equals 0, that means the non-dispersive point in the phase speed is a critical point in the phase speed, right? Cp prime equals 0. So this is the group velocity and phase velocity for the capillary gravity waves in deep water. They have intersection point at wave number k equals 0, corresponding to the minima of the phase speed. So because at this point group speed equals the phase speed, we can expect the solitary waves bifurcating from this point and exist below this point, because all the speeds are equal, linearly speaking. Right? All right. So that's the basic knowledge for the nonlinear waves, and we will focus on the wave number k equals 0 for capillary gravity waves. All right, so now let's move on to the weakly nonlinear theory. The weakly nonlinear theory for the wave packet solitary waves, the conventional wisdom in the weakly, the conventional wisdom for the wave packet solitary wave is the nonlinear Schrodinger equation. So the nonlinear Schrodinger equation is a universal model, appears in many contexts in science and in physics, including the nonlinear optics, plasma physics, and hydrodynamics. And nonlinear Schrodinger equation provides a canonical description for the evolution of the envelope of a quasi-monochromatic plane wave propagating in a weakly nonlinear dispersive media. And the last can be used to predict the existence of solitary waves as well as the Benjamin-Fair instability. Right? And a lot of dynamical behavior of the wave packet solitary waves can be understood and compared with the NLS. All right. Let's start with the 1+1 NLS. Now take a monochromatic wave and multiply by a small amplitude, slow varying envelope. Then you plug the ansatz into the water wave problem that you're going to solve into the your favorite model, irrotational Euler equation with free surface. Then you do Stokes expansion and equate-like powers of epsilon. All right. For the first order of epsilon, you obtain the dispersion relation. For the second order of epsilon, you obtain the group velocity and the period doubling, the second harmonic generation. And for the third order of epsilon, you obtain the nonlinear Schrodinger equation. So lambda 1 is the linear coefficient, and the gamma is called the Stokes nonlinearity, which changes the frequency in the mean field approximation. This is different from the Burgers equation, the Burgers type nonlinearity in the KdV equation. It changes the frequency in a way that proportional to the amplitude squared. And there are two combinations of lambda 1 and the gamma. So if lambda 1 and gamma are of the same sign, this NLS is called focusing NLS, cubic focusing NLS, and you will have such type bright soliton, and the waves are in the Benjamin-Fair unstable regime. So you have a wave train, then you perturb the wave train, use a long wave, then you will quickly see the focusing phenomenon. So this is a Benjamin-Fair instability, and they're quite simple argument for the Benjamin-Fair instability. You have a wave train, then you take a crust, and you move the crust a little bit, then you increase the wave number ahead of you and decrease the wave number behind you. And these little feedbacks in gamma will increase the amplitude ahead of you. So that's the Benjamin-Finn instability. So if lambda 1 and gamma are of the different sign, then you can have dark soliton solution, and the waves are in the Benjamin-Finn stable regime. So this is 1 plus 1 NLS. All right, now let's talk about 2 plus 1 NLS. 2 plus 1 NLS is a very different animal. 2 plus 1 NLS, now you have both X and Y modulations. Suppose we consider the capillary gravity wave in deep water, and the carrier wave only propagate in the X direction. Then you plug the ansatz into the problem, and you will find the 2 plus 1 NLS. So if you work in the capillary gravity wave in finite depths of the fluid, then what you get is the Benny-Roskis-Davis-Watson system. You couple it with the main flow, but in deep water, the main flow degenerates to the next order. So it's just the cubic NLS. All right, so now you have two linear coefficients, lambda 1 and lambda 2. They are very different animals. Lambda 2 is always positive for whatever water wave problems that you give me. Lambda 2 is essentially always positive because it's the group speed divided by the wave number. This is called geometric focusing. That means you have a wavefront like this, and the wavefront curved a little bit like this. Then the geometric focusing tells you the amplitude ahead of you will increase a little bit, then focuses, then curved more and focuses more. The wave tends to break up. And lambda 1 is very different. Lambda 1 can be negotiable. Lambda 1 means that depending on whether the group's velocity in the x direction is increasing or decreasing. Right? Gamma is the nonlinearity. There are two branches of gamma. This is two branches of gamma separated by the wave number square root 2/2 corresponding to the Wilton ripple under my non-dimensionalization. We are interested in the right branch because we're interested in the wave number k equals 1, which is precisely the regime for the generation of wind ripples and the solitary waves, right? So in the regime that we are interested, wave number k in the vicinity of wave number k equals 1, lambda 1, lambda 2, gamma are all positive. So this is elliptic cubic NLS. All right. So 2 plus 1 is a very interesting equation because 2 plus 1 NLS has finite time block solution. So there's very elegant argument shows if the Hamiltonian of the initial condition is negative, if this quantity is negative, then the solution focuses and blow up in finite time. So for 2 plus 1 NLS. So this is it's a very special focusing mechanism, blow up mechanism for the equation because other singularities may occur beforehand or before this focusing singularity. And if you follow the argument, you will see that if this quantity is positive initial data, then the wave tends to spread out. If this quantity is negative, it blows up, focuses and blows up in finite time. Then, if quantity is 0 initially, then this is called a critical state, right? Because if you slightly perturb it, then the energy becomes negative or positive. They either focus and blows up in finite time or spread out. Right? So it is obvious that question.
Sorry, can you just clarify what's different about this argument in 1D and
2D,
2D?
1D, you cannot have this relationship. So this one. So if you do,
the key is the right-hand side has to be a constant of motion.
That's right.
The E, and in one space dimension,
That's
G double prime
that's
is
right.
not equal to a constant of motion.
That's right.
That's what you need.
But I thought
Sorry?
So E there is a Hamiltonian.
It's a constant of motion is the key factor here, okay?
Yeah, but
Yeah.
so it's a Hamiltonian in 1D is still the constant of motion.
That's right, but G double prime is not equal to Hamiltonian in that case.
That's right. That's right.
So that's the key.
So the direction doesn't hold. And the bright soliton is stable in 1D because it's the minima in phase space, something like that, in the Lyapunov sense. All right. So,
Sorry, I had a question. Can you tell us what it means for a wave to collapse to a point?
oh, the value becomes infinite.
At a certain value of x and y?
Yeah, it becomes delta function.
So you don't know which value of x and y, but
No.
some value of x
That's
and
right.
y.
That's right.
Okay. Depends on
So-
the initial I guess.
Wave collapse means
Well, there's collapse and there's blow up. And here they both occur.
so collapse means the value becomes infinite, and
No, blow up means the value becomes infinite. Collapse means the support shrinks.
okay. All right.
There's no guarantee that the collapse occurs at the time dictated by this. It just says.
No.
Something bad has to happen.
Before this
equal to.
focusing. That's right. That's right. So that's the remark.
Yes, right.
All right. So it is important to find the critical states, right, where the energy is zero. So it's quite simple to see that all the fully localized traveling wave solution satisfies E equals 0, because if for the traveling wave solution this quantity is time independent, so G second prime is 0, so E equals 0. So it's very simple. So all the fully localized traveling wave solution satisfies this condition, E equals 0. So this solution has been found many years ago, in 1964, by the people in nonlinear optics. So by solving the following nonlinear ODE, and this nonlinear ODE is a radiosymmetric solution of the Laplace equation, and not Laplace equation, but the cubic NLS. And this solution has countably many solutions, so indexed by the number of the roots. So this is the first mode, which is called Towns profiles in nonlinear optics, or called the ground state in quantum mechanics, which is positive, definitely, pretty much like Gaussian. And the second mode is a red one, and you can see it crosses the horizontal axis once. And the third one is the dark one, which crosses the horizontal axis twice. So, and so on. So these are the solutions have zero energy in NLS. All right, so now the condition for the existence of wave packet solitary waves is you need a minima of, or you have extrema at finite wave number, and then at this critical point the NLS is focusing. Why is that? Because the free surface can be approximated by the NLS solution coupled with the traveling wave, coupled with the monochromatic wave, when the amplitude epsilon is small. Suppose you have a traveling wave A, which is fully localized, then this solution can be used to approximate the solution in the primitive equation, which propagate at the because the group speed equals phase speed, so Cp equals Cg, then this one propagate at certain speed and decay in space. So this is an approximation for the solitary waves. So that's a condition. And for the resonance issue, you need a global extrema for Cp. Otherwise, it will resonate with linear waves, and what you see is the generalized solitary wave. But in 3D, you need a minimum, global minimum. The global maxima also has resonance. All right, let's start with the capillary gravity wave. So what is capillary gravity wave? The wind ripples, right? You can imagine that wind blowing on the water surface, you will see a lot of ripples that generated by the wind. The typical wavelength for wind ripples are about several centimeters, so very short. in this very short length scale, the effects due to gravity and surface tension are equally important. So, so that means in your PDEs that you're going to solve, you have to include both of them, right? You have to include both gravity and the surface tension. Why do we care about capillary gravity waves? One reason is capillary gravity waves are the main scatterers in microwave radar remote sensing, because the wind data on the sea surface is important. The way to measure the wind data is to measure the ripples that forced by the wind in the satellite, and this is very the equipment in the satellite, the radar in the satellites to measure the ripples are called scatterometers. This is a very special radar. These radar may not be able to capture large waves like tsunami, but they are very sensitive to capillary gravity waves. The reason is the wavelength of this radar is about 3 to 7 centimeters. So they are very similar to the wavelengths of the capillary gravity wave. All right. Number two, the applied mathematicians are very interested in capillary gravity waves. The reason is the onset mechanism of the instability between two immiscible fluids under shear current or under forcing and dissipation is a poorly understood problem, right? And the linear theory doesn't give you the right answer. The linear theory overestimates the energy needed for generation of wind ripples. So the linear theory tells you you need a quite strong wind to see the ripples, but the real experiment shows you only need a very light wind. So that means the nonlinear effects, nonlinear dynamics, may play an important role in the generation of wind ripples. In particular, the coherent structures nonlinear coherent structures that propagates with the speed lower than the speed that's allowed by the linear theory might be the first excited mode for triggering instability. That's another reason.
Sorry, triggering what instability?
To see the ripples, the instability of the interface.
You're talking about a wind shearing over water.
Yeah.
And the first set of instability is due to what?
Maybe the nonlinear coherent structure.
Coherent structure.
Yeah.
You mean like Kelvin-Helmholtz instability?
There is no evidence.
No, there is no evidence of that at all. That's absolutely not true.
But linear theory is not.
Well, yes, linear theory is quite adequate.
That's right.
I mean, we've done in the past a fair bit of work on things like the minimum wind speed to generate waves, and that agrees very well with the worldly observations of Donald and Kama from the 80s.
Because normally one of the major things that happens in that sort of a situation is either tunnel selecting waves in the upper atmosphere interacting with surface waves, or the modes like a Kelvin-Helmholtz mode. Mm-hmm. Those are the two things that gives you these ripples, initiation to the ripples.
All right. Okay.
Yes.
All right. So the last reason is capillary gravity solitary waves is a new kind of solitary waves. For the pure gravity wave, solitary waves can only exist in shallow water regime and can only decay in the wave propagation direction, cannot decay in the transverse direction. But under the joint effects of gravity and the surface tension, solitary waves can decay in all spatial directions, propagating without changing form. So these solutions are called lump solutions. All right, so I want to talk about how to compute efficiently and accurately compute these waves, and what is the dynamics of these waves, and some focusing dynamics. All right, so this is a PDE that we are going to solve incompressible inviscid rotational flow with free surface, and I think everyone knows this. And the only thing I want to say is I make deep water assumption. So I make h infinity. So this is a physical assumption because the typical wavelength of capillary gravity wave is about several centimeters, 1 or 2 centimeters. So if the fluid is deeper than several centimeters, the free surface cannot fuse the body. So why not just make dipole assumption? All right, so because this is the numerical week, so I would like to talk something about how to numerically compute these waves. So the way I compute solitary waves is capillary gravity waves is I write down the Hamiltonian for the surface water wave problem. And here G is the Dirichlet-Neumann operator. Then because this is an analytical operator under some condition, then we can Taylor expand the Dirichlet-Neumann operator. Then I truncate the Dirichlet-Neumann operator to some order, then take variational derivative. So that's the way I compute the solitary waves, compute the dynamics or compute the capillary gravity waves. So I would like to give 2 comments of my numerical method. Number 1, a lot of computation, when they truncate the Dirichlet-Neumann operator, they truncate the Dirichlet-Neumann operator in the kinematic and dynamical boundary condition. They don't truncate the Dirichlet-Neumann operator in the Hamiltonian. So the reason that I truncate the Dirichlet-Neumann in the Hamiltonian, that's because you can get to the Hamiltonian structure of the PDE for free. And the Hamiltonian is important for the inverse surface water wave problem because it relates to the stability property of the traveling waves to the superharmonic perturbation. And the second comment is I don't truncate the terms that you don't have to truncate. So the surface tension term is also a fully nonlinear term. And because I truncate the Dirichlet-Neumann operator to some order, then people would like to say, because you do that, you have to truncate the surface tension term up to the same order for the sake of consistency. But consistency is sort of disease. If you truncate the surface tension term, then you will find that the numerics becomes much worse. So if the surface tension, the fully nonlinear surface tension term regularize the computation very well, just to keep it.
May I ask why the coefficient is 2?
Yeah, because they have 1/2 here.
No, but why there's no I formulate the question wrong. There's some non-dimensionalization going on here?
Yeah, I remove all the coefficients.
All of them?
Yeah, all of them.
Okay.
So I remove all of them. So no G, no surface tension.
Non-dimensionalized.
The one number.
Non-dimensionalized.
One number is 1.
Well, that's along with Higgins standard non-dimensionalization. G is 1 and the wavelength is 2 pi.
One number is fixed now as well.
Okay.
So I didn't understand, okay.
No, it means surface tension is very strong in this problem.
Okay.
It's not a parameter. So. All right, so now I have to decide for which order to truncate, right? So this is for 1D problem. I can do the computation up to machine accuracy. So the numerical methods are very accurate. You can do conformal map, or you can use boundary integral method. So this is the bifurcation diagram for depression capillary gravity solitary waves, and the circles are the solution for Euler computation. And these curves with different colors are the computation using different orders of truncation. It is obvious that the quadratic and the quartic truncation models are not good, but cubic and quintic truncation models are good. So I pick the cubic truncation model. So that's the way I decide how to truncate the Dirichlet-Neumann operator.
So it oscillates, right?
Hmm?
So if I see it correct, cubic
Cu-
good, and then quartic.
No. Cubic is the dark line is good,
Yeah.
and the red one is quintic.
But the quartic
looks worse than cubic, is that correct?
That's right.
And it oscillates. Blue on top is quadratic, then it goes below.
The reason is for quartic model, quartic means in the PDE. Then in the Hamiltonian is quintic, right? For the Hamiltonian quintic, that you have something like eta cube, you see.
Yeah.
And because depression wave is quite negative, so this quantity might be negative. So that's the reason why it becomes worse.
Is the behavior the same for very small
Yeah.
speeds?
So
closer
when
to
the amplitude is small, they're all good.
Is it still the same ordering that quartic is worse than cubic?
No, no. When the
So
amplitude
what do you
is
think if you
small,
go to sixth order,
sixth order is also not very. Sixth order is not very good, but you know, if you expand a lot turns, then you cannot compute a lot of large amplitude waves. So that's the problem. And I have to say the sixth order is okay. It's okay. All right. Right, so now I can compute the plane waves and the lump solutions. So plane wave is you use the 1+1 and analyze soliton to prepare the initial data and you send it to the Newton algorithm, then you can have the solution, right? And you will have two branches, elevation branch with the positive central point and depression branch with the negative central point. Also, you will have lump solutions and you use the ground state of the NLS to prepare the initial data. And you will have also you will have two branches of solutions. All right, so we will focus on the lump solution because we were doing three-dimensional problem and plane solitary waves are unstable to the transverse perturbation. And we will focus on the lump solution. They serve attractors in the dynamical system, in the inviscid computation. All right, so because these waves are constructed based on the ground state, so ground state is unstable, right? Ground state, the small perturbation leads to either blow up or spread out. So the question is, how about the water wave problem, the full water wave problem? Are these solutions stable or not? So now I take a small amplitude depression solitary wave, depression lump solutions, then I perturb it such that the energy of the NLS, underlying NLS, become positive. Then NLS tells you it will focus and it will spread out. Let's see what's going to happen in the water wave problem. The water wave disperse out very quickly, right? So that means NLS predicts the instability quite well. Now, I take the same solution, then I perturb it in a different way. I perturb it such that the NLS energy becomes negative. NLS tells you it will focus and blow up infinite, it will collapse infinite time, right? So now let's see what's going to happen for the water wave in the water wave problem. It focuses initially, but doesn't blow up. It becomes time periodic breather solution, right? Because when the amplitude becomes large, the NLS is no longer the right model for the water wave, right? Because the focus is the amplitude increase. All right. So let's summarize the stability property for the lump solutions. Now you have two branches, elevation and depression branch. This is Hamiltonian versus speed. And both branches, this is the blue curve is for the elevation branch and this is for depression branch. And both curve has minima in the bifurcation diagram where the stability property may change. So it turns out all the solitary waves are unstable except the moderate amplitude depression solitary waves, the lump solutions. They either disperse out or become a time periodic breather solution around the stable state. So they all become something like this one. So that's the stability.
So there's no change of stability at the minimum?
There's a change of stability for the depression wave.
There is.
There's no change of stability for the elevation wave. The stability change is a necessary condition, not sufficient.
I'm sorry, the minimum is, you mean the minimum is necessary?
Is a necessary condition. Is a necessary condition, but not sufficient.
Okay.
All right. Now I want to say these large amplitude solitary waves is a global attractors in the dynamical system. I'll show you some numerical experiments. Number one is this is the solitary waves that construct based on the second eigenmode of the NLS, 2 plus 1 NLS, because 2 plus 1 NLS has infinite many radiosymmetric modes, right? So you can construct solution based on the first eigenmode, or you can based on other solutions. So this is based on the second mode, second solution, and this is the contour. And very complicated wave pattern. And I want to show you these waves are very unstable, and the long-time dynamics is they will become a bunch of depression solitary waves that construct based on the ground state. So run the program, nothing happens because the traveling wave, then gradually there's instability, there's symmetry breaking instability. And what you see is that after very complicated interactions, what you see is it breaks down, the structure breaks down and become a bunch of depression solitary waves with different speeds. This is the one example for the dynamics, focusing dynamics of the capillary gravity. And the next example is motivated by the nonlinear optics. So,
Got a question?
question.
The numerics in the movie, what are you doing at the boundaries?
Periodic boundary conditions.
So what happened to recurrence?
Yeah, but the large amplitude depression wave is stable. So even you have some ripples, it's okay.
But he's not solving an LS, right? So
No, yeah.
this is the water wave itself. So why do you think there's recurrence? The truncation?
Well, if you want to solve it faithfully, you want to mimic the properties.
What do you mean by recurrence? What do you mean by recurrence? You mean going out one side and coming back in the
Yeah.
other? Or something
Well, if he's
different?
solving the periodic
Yeah, that's what I would expect too. I didn't know what you meant by recurrence.
yeah, that's what I meant.
Yeah, why isn't the wave coming back in?
Well,
Just put it in the
when
frame
you
of
stop,
reference.
Yeah, I'm moving with the
I
frame.
think he means it comes back to the original state. Is that
or
what you mean?
close, yeah.
Oh, that's point for recurrence. That will take a long time.
Well, right, but it seemed like it was settling down to other things that would not come back to. I mean, it can't settle down to something else. That's my point.
It didn't look periodic.
Is what you're showing the actual size of the computational domain, or is it bigger than you just zoomed in?
It's bigger.
Okay, that's fine. So your period is bigger than minus 60 to 60.
No, much bigger.
So it doesn't count yet.
Now, one other question. If you perturb the initial state of that slightly, what happens?
The same thing. Always become depression lumps.
You count
So
how many?
it's sort of
Hmm?
in the
You count how many? You got 4, I think, from this one.
It depends on the energy you have, right?
Can you draw that correlation?
That is, when we give you an energy, can you count the number of lumps asymptotic?
No, because you have a lot of ripples. So you cannot exactly know how many lumps you will have.
Your point here is that this lump solution is unstable, but then the end of your argument is it ends up with a bunch of lump solutions which are all stable.
Stable. So
Which is it?
So these solutions are stable. So you can have a lot of solutions of, based on the different modes of NLS. So NLS have a lot of solutions, right? Then you can prepare the initial data by superposing the ground state and the carrier wave as the initial data, and you will have solution. The solution looks like this.
Well, you see, have you read the works of Philip Safran?
Say it again.
Have you read the works of Philip Safran? Safran at Caltech.
Which one in particular?
Well, the thing is, his argument was always, a lot of argument with him about that NLS has overabundance amount of solutions. And it all depends which one you pick. And a lot of them don't even physically have any meaning. Well, that's the reason he went to his approach of looking at nonlinear, three-dimensional nonlinear Stokes waves and other ones. He always thought slight perturbation in the initial state will give you a completely different solution. And he himself actually admitting that there are many solutions to this problem. And if you get that, that's essentially the ODE that he has is an elliptic equation, like a Weierstrass elliptic function. And for that, slight perturbation in the argument will give you a completely different solution.
Excuse me. Can I ask a question? Because I don't understand how you can obtain a nonlinear Freudian equation in this type of problem. Because you have three wave interactions in the graph capillary wave problem. So what have you? Do you assume that they are not existing? Do you ignore them in the derivation of the NLS equation?
Yeah, I fixed the wave number k equals 1.
But there's an infinite number of three wave interactions.
But he showed the picture, and his bond number is much greater than that Wilton ripple, or the three-wave interaction. He's choosing a bond number much higher.
He's choosing bond number 1.
Well,
yeah, that's what he's doing. Bond number 1.
That was supposed to represent very high bond number. But there was a diagram there where he showed the three-wave interaction, and he was much higher than that. And so, the NLS is around a certain wave number.
No, but this is around the minimum of the phase speed, okay? So there are certainly strong nonlinear three-wave interactions around the minimum of the phase speed.
Oh, you mean the higher one, just not traveling with the thresholds. The instant ones. 1, 3, 2, 3.
Around the minimum of the phase speed, there are lots of three-wave interactions. Believe me, I looked at them.
Okay. So the way that he can get to an NLS is he assumes his data is narrow banded.
Yes,
so that it'll support it near k equals 1.
Yeah, but that solution can only
So
be
there aren't the
developed
other
for a very
triads
short time. That's right. Because then you start kicking other things, and then you get three-wave interaction. That's much more important than this higher order thing.
And they will sort of excite other modes.
Maybe.
So, but then he solves untruncated, almost untruncated original water wave equations, and he does not see these triads.
Yeah.
Maybe they are outside the domain in
not around the minimum, not around the minimum phase speed.
Peter, he's solving the full Euler equation.
Yeah, I know.
Not NLS. So.
But you don't get the same. You get recurrence. You get other things happening. I mean, you get typical recurrence, of course, with a three-wave interaction problem.
Well, there's a lot of material for the blog for this meeting.
So I'm just wondering, I mean, I may be completely wrong, but I did the problem myself 20 years ago, but I started with three-wave interactions. Okay?
All right.
The Karov equation for the three waves.
We save the rest for the half an hour between. Why'd you go ahead?
All right. So in nonlinear optics, the 2+1 so NLS, cubic NLS is also the fundamental equation. So there are two kinds of nonlinear optics. The first nonlinear optics is you can send light into the fiber. So it's called fiber optics. the fiber optics, the governing equation is the 1 + 1 cubic NLS. So no, basically speaking, it's 1 + 1 NLS, because most recently they use Ginsburg-Landau equations. They add dissipation, saturation, and the higher order dispersion. But basically speaking, it's 1 + 1 NLS. And this is the fiber optics. The second one is called, you can directly shoot the laser into any material. You can shoot the laser into water. Then the governing equation is 2 + 1 NLS. So it turns out that there are two communities who are doing nonlinear optics, who are doing cubic NLS. The first one is the water wave group and the nonlinear optics groups. They have talk, right? Most of the cross-section talk have focused on the 1 + 1 NLS. But it turns out that the 1 + 1 NLS is not my interesting. I'm interested in 2 + 1 NLS. So I shoot light directly into water. Okay, so I shoot light into any material, and the z direction is the time-like direction, and the xy direction in the cross-section profile is the space-like direction. So now you have the 2 + 1 NLS, which is so now you don't have λ1, λ2, because in the isentropic media, you cannot tell the difference between x and y, and the dispersion and the wave propagation direction is perpendicular to xy plane. That's the fundamental difference between the nonlinear optics and water wave. In water waves, the wave propagation direction is in the x direction. So in water wave problem, λ1 and λ2 are different. One is self-interaction focusing, and another one is the geometric focusing. And in the nonlinear optics, both x and y are geometric focusing. So that's a fundamental difference. Now the question is, the first question is, why is light nonlinear? It turns out it's not in the vacuum, right? But it does become nonlinear in any other material, which is called the Kerr effect in a Kerr material. The gamma is positive. Gamma is called the nonlinear index of reflection. But gamma is extremely small under dimensional variables. Gamma in water, gamma is 10 to the minus 22, which means the change of the speed of light having to do with the nonlinear effect is very, very small. Right. Now, if you want to see the nonlinear phenomena, the way you can do is you can boost the amplitude. Hey, well, gamma can be engineered to be essentially whatever you want in the fiber optics. Why is that? Because you can make the cross-section of the fiber using different materials, have transverse eigenmode, and decide how they disperse. But if you shoot light into water, you cannot change gamma. The only thing if you want to see the nonlinear effect, the only thing you can do is boost the amplitude of A. Right. Okay. So let me show you some orders of magnitude to give you some physical intuition.
Just before you continue, excuse me. So if you shoot laser beam into water, there will be dissipation.
Yes.
Which will be normally stronger than
That's
the
right.
linear effect. Yes.
That's right. But I only shoot the laser, a very strong laser, for several centimeters.
Oh, okay.
That's the experiment. So if you travel very long distance, even though this light is extremely fast, you will have dissipation, and you won't see the focusing phenomenon. Right. Thanks. Okay. So some orders of magnitude. So for pure gravity wave on deep water, so lambda, the wavelength is about 100 meters, and epsilon is 0.1. That means in one wave packet, you only have 10 crests, right? And if you want to feel the nonlinear effect, the wave has to propagate for 10,000 meters. And you send the light on the water onto the water, and sun shining on the water, and the lambda is quite small, 500 nanometer, and the epsilon is extremely small. Epsilon square is 10 to the minus 16. That means if you want to feel the nonlinearity, the light has to travel about 10 to 9 meters. So in most cases, light is linear. You will see nothing. Now you send light, use a pulse laser. So you send the light like a pulse. Now you don't have, because the laser is very strong, you don't have the continuous laser because otherwise you don't have enough electricity. So the laser has a peak power of 100 megawatts. 1 megawatt equals 1 million watts. So it's very strong laser beam, and it shoot light into water. And the length scale is about 800 nanometer. And epsilon square is 10 to the minus 5. Aha, it's very close to water wave. And if you want to fuse the nonlinearity, the light has to travel about 0.1 meters.
So how do you compute the nonlinear length?
Because the length is L divided by epsilon. So L divided by epsilon.
Normally you should
Then you need only need a lambda divided by epsilon squared.
Lambda divided by epsilon squared.
Yeah. That's right. Yeah.
So let's calculate it now.
I'm sorry, there is other some experiments with this laser.
Yes.
Yes. Because vaporing small particles in the liquid or something like this leads to bubbling and other catastrophic.
So this is experiment done.
Yes,
So now this is an experiment done in Tel Aviv by the group of Gaudi Fibish. So now you send the pulse laser into the water, and if the pulse laser is strong enough, and you send the light into water, if the initial profile of the beam is Gaussian, if the laser is strong enough, what you see is the light focuses to Tom's profile. So focus to a point. If the initial beam is super Gaussian, the dynamical behavior is very different. It focuses on a ring. So that's the experiment done in the lab. They shoot light into water using super Gaussian initial data, and this is a super Gaussian initial data profile. And we'll see when z equals 1.3 centimeters, you will clearly see the ring focusing, and the 2 centimeters, 3 centimeters, and 4.3 centimeters. So finally it breaks up.
Depth into the fluid.
That's right. So z direction is the time-like direction. Z direction is time-like direction. So finally it becomes filamentation. They call it filamentation in nonlinear optics. So this is the numerical experiment. They can predict how many filamentations they can have. All right, so why do you have different phenomena between Gaussian and the super Gaussian? So there's a very simple geometric argument. So this is initial beam is Gaussian, and this is a super Gaussian. So suppose your initial beam is very, very strong. So the nonlinear effect dominates over the linear diffraction. So you can get rid of the Laplacian in the cubic NLS, and the left part you can solve explicitly. So this is these are the solution for the cubic NLS without Laplacian. So the vertical lines are faces, and the horizontal curves are the rays. So for the Gaussian beam, it is obvious that the rays focus to a point very quickly, but for the super Gaussian beam, the rays focus to a point much, much slower. So that's the description.
So in both cases, the Laplacian term disappears, or only in the Gaussian case?
Both disappear. So if the A is very, very large, then the nonlinear effects dominates over the linear effects. So that's just the explanation, not the real proof. All right. Okay, so what's going to happen after the strong focusing in nonlinear optics? People in nonlinear optics don't like blow up, right? NLS blows up, but people in nonlinear optics don't like blow up. What they say is high order process such as plasma generation hard to collapse because you send a very strong light into the fiber, then you heat the fiber, and the thermal effects become much more important. So the class-mark generation should be considered. And there may be azimuthal instability and filamentations. As you see in the experiment is the filamentations. Those highlight spots are called filamentations. And they also have a very fancy name. They will say that, oh, these waves reach the supercontinuum. The supercontinuum, as I can tell, so it's a spectral broadening process. If you look at the spectrum in the Fourier space, it broadens quite a bit, very quickly.
Irreversible.
Irreversible, okay. I didn't know that. So, anyway, okay. So now, because NLS is the fundamental model for nonlinear optics, also the fundamental model for water wave, for capillary gravity wave. So one natural question is, can we observe the same phenomena in water waves, right? Okay. So now we do the numerical experiment for the water waves. Then I prepare the initial data using super Gaussian. What is super Gaussian? E to the minus r to the fourth. Then coupled with the carrier wave, then send it. This is just a time-dependent computation, very simple, right? Nothing else. Now you do the experiment, you will quickly, what you see is you will quickly see the second harmonic generation that gets through a head, and you will clearly see the ring focusing phenomena. And finally, it breaks up into a bunch of depression lumps and breezes and some dispersion. So I'll show you again. You'll see the second harmonic generation. The left part is very nonlinear, so ring focusing and breaks down. All right, now you can play with the game. You can use the super square as the initial data and run the program. Now they will focus on the square. Now they focus on the square, not on the ring.
You could use this in cryptography. You send letters and nobody can tell what it is until it focuses.
That's right. All right, finally it breaks down into a bunch of depression waves and the breezes. All right, this is inviscid computation. Right, this is inviscid computation, but because capillary gravity waves, the length scale is very small, then the viscous effect is important. So, but water is, if you want to do real experiment, water is still too viscous to see the ring focusing, but you can use other material, other fluid. You can use this is the numerical simulation for, use this model to model mercury. Mercury has very large density, very small surface tension, and if you compute the Reynolds number, then the Reynolds number is quite large. So then you can do the numerical experiments, and this is for Gaussian, and this is for super Gaussian. Initially, they have the same Hamiltonian energy, and you run the program, you will see the fundamental difference. For Gaussian, you will see the focus to a point, focus in a point, but for super Gaussian, you will see clearly the ring focus. So that's the fundamental difference, right? And finally, it breaks up into a bunch of depression waves and breezes. So, okay, I'll finish that. Okay. So the focus and cubic analysis, and let's conclude. So the focus and cubic analysis is essential to understand the existence of solitary waves as well. Initial linear and nonlinear focusing for lumps and breezes, but dispersion has a long-time dynamics. And ring-shaped focusing should be observable in Mercury, on Earth, or you can do the experiment in the spacecraft because you can decrease the gravity by several orders of magnitudes, and you can increase the Reynolds number by several orders of magnitude. Then it's almost inviscid computation. That's it. I don't have time to go to the fracture gravity waves, but anyway.
Right at the end, you said Mercury has high density, low surface tension. But Mercury has very high surface tension.
Oh, Mercury has, that's right. Mercury has very high, sorry. Mercury has very, Low viscosity. Sorry, low viscosity.
So, you started with plain solitary waves, which are transversally unstable. So, what is the typical scale of transverse instability? And so people do experiments in very narrow tanks, and maybe this scale could be larger than the scale of their tanks.
Yes.
So what is the scale?
So
because it's much larger than the wavelengths, but what it is?
I don't remember correctly. Do you know? It's for 2+1 NLS. If I rescale everything, the wavelength in the transverse direction is square root of 3. So for NLS, for this NLS.
No, I'm not speaking about this NLS.
No, I know. The NLS predicts very well of the transverse instability for the capillary gravity.
Yes.
1+1, 1D
And
NLS.
I'm asking, what is this scale? It is much larger than the wavelengths, but how big it is?
The NLS doesn't predict that. It's a long wave instability.
It's a long wave instability.
It's a long wave instability. It can be found as an expansion in the transverse wave number, right?
Yes, exactly. Yeah.
But
it's
this
still
analysis doesn't give you the point where it peaks. So it doesn't give you the point.
So my question is, so I put it in a different way. So that this scale is large compared to wavelengths.
Yeah.
And people do experiments, so in capillary waves in very narrow tanks. It might be that they cannot see these structures also because it's just different parameter range. So that's
The length scale is, I know this is not precise, but qualitatively speaking, is the length scale that is the scaling that gives you the lumps. It is not a precise, I know, but it is not exact, but it is the right scaling that will give you the lumps.
Sure, but the lump is roughly has an order of magnitude larger transverse scale.
Yes.
So this is roughly.
Yes, that's what happens.
Yeah. Okay.
I think the problem with the experiment, I'm not an experimentalist, but I'm convinced that experiments without viscosity, these things we don't see without viscosity or forcing. This is it.
Yeah.
So unless something happens, then you won't see.
So I'm familiar with the experiments in the tank and capillary gravity range. Nobody has ever seen anything.
Except Zhan. Zhan claims that these are, I raised that question in my talk, whether this is true or false.
I don't know.
Yeah. I agree with you.
Thank you.
Thank our speaker again and go have a break.